Hello, good afternoon. I'm Olga Tischlingerová, and along with my colleagues Marko Naninga and Ed Morris, we welcome you to this webinar. For your information, we are recording this session, and the recording will be available early next week should you wish to listen back or show to your colleagues who perhaps were not able to join today. If you have a question, you can type it in a question box, as everyone's microphone will be muted. And after the presentation is finished, we will answer the questions. That's all from me for now. Marko, over to you. Okay, Marko, so if you are ready, you can start.
Yes, thank you, Olga. I am Marko Naninga, the product specialist for ATS Inspect, one of our products. As said here already on the slide, have a lot of experience with that product. I'll be doing this webinar together with my colleague Ed Morris, our dimensional quality expert. Maybe Ed, you can introduce yourself a little bit.
Hello, I'm Ed Morris. I work mostly with dimensional data and a little bit with attribute data, whereas Marko's the opposite. So we make a good team. As it says in the on the slide there, decades of experience, mostly in manufacturing aerospace or manufacturing vehicles. Okay.
All right, thank you, Ed. So the agenda for today is to talk about the hidden benefits of combining process and quality data. When we talk about quality data, we mean both attribute and dimensional data, how it can aid the continuous improvement initiatives, and we will go through some real-world examples of integration of the various data that we have done for our existing customers. And then we'll end with a Q&A, of course. So let's get going. We have three scenarios prepared for you, starting with a very simple one and then going a bit more in depth after this one. So for this one, we are reading in dimensional data. We use a product called CM4D for that, but it can be any product that can handle that kind of data. The data is received and evaluated. For any value that is outside of the tolerance, a defect is being created in the software that we use to capture the attributes quality data that's Inspect in this example. The flow, how that goes, is shown here. So just in short, the measurement files are sent to CM4D. It does the import and analysis of the data. For anything that's out of tolerance, it sends the data to Inspect, that receives the data. It creates a defect on the exact XYZ coordinate, or XY if it's 2D, on the appropriate view. And those defects are combined with the defects that are captured during the normal attribute inspection process and can be shown in reporting. That's in a nutshell how this example works. For CM4D, we have a slide here describing how it handles the data. So over to Ed for CM4D.
So, I mean, we've used CM4D for this example, but it could be any dimensional management system. And it's not just, we shouldn't just consider alarming on out of tolerance. You could or should consider alarming on statistical measures such as low CPK, low repeatability, bad measuring, issues like that. But whenever the system sees an issue, in this case, I've just asked it to show me where those issues are on the CAD model, and then it messages the attribute system immediately so that we can combine the visual inspection from the guy on the shop floor who may have noted, hey, there's a scratch here somewhere, or this is a bit loose. And we're comparing that with our dimensional data and our statistical process control so that we get that sort of joining up of two-part datas that we very rarely see joined up today. So if you want to carry on there, Marco.
Yes, thank you, Ed. So when the data is sent from the dimensional software, in this example CM4D, to the attribute quality software inspected this example, the data has to be picked up. For the example that we have, we are using the inspect.com service, where we can see the data that is coming in from CM4D. It stores the data in the database linked to the serial number that we also get with the data. We have the XYZ coordinates, some comments that have the nominals and the tolerances, and then depending on the logic in the store procedure that handles this data, we can store the data, for example, to be shown like this, where we have a defect with basically all the information that we get from the dimensional system in the reporting for the attribute product. So going from there to a little bit more of a complex setup is, well, really data flowing the other way. So in this example, we are entering dimensional data in the attribute quality inspection system. It can be either way. In this example, in the next screenshot, it's being asked as questions to the operator, where they enter in the measurements. Those measurements are then sent to the dimensional quality system. In this case, because there was no direct integration possible, we are using a product called ATS Bus to do the integration part and to share the data. And what it does at the end is CM4D analyzes the data. It creates a PDF report, which the operator then can open either on the shop floor, or anybody who is interested in the report can find it on the network. So what we've done for this example, and of course this is all fake data, no real customer data. The example here is just a Lego man, where we are doing measurements of various characteristics. The measurements are being entered manually, and like I said, the data is then sent to the dimensional quality system and handled in that system. To get the data to there, we had to use a integration solution. For that solution, we've chosen to use ATS Bus, where the data is picked up from inspect via a TCP channel. It picks up the data. The available data is a lot more than what CM4D, the dimensional system, actually needs. So in the bus, we use an XSLT transformation to strip unneeded data and create a much smaller XML file with only the data that is useful for CM4D, for the dimensional system. That file is stored in a network location that is monitored by CM4D, that then picks up the data and stores it in the database. And as is described here, it can also send a return message if the data is being picked up. So over to you, Ed, for the CM4D part.
Yes, I say we've used CM4D for this example. It could be any of the dimensional measuring systems that are out there. In this case, the part of CM4D is called Datasmith. It reads in the XML file directly. The great thing about the Datasmith service from the CM4D side that we like is that it can read any file. So it's a lot of the systems that we work with, they're quite, you know, if you buy, say, from Hexagon, they tie you into QDAS. If you buy from Zeiss, they try to tie you into Calypso. GOM tend to tie you into their software. And the nice thing about the Datasmith service is that it can read all of those data types. So we can actually pull any dimensional or attribute measurements into one database, convert all those apple pears and bananas into apples, and then we can actually do some really good analysis. Okay, so in this case, we've measured the Lego man, we get an XML file, the system automatically recognizes that a new piece of data has appeared, and it will then automatically analyze the last 50 Lego men. Okay, and then if necessary, it will automatically message the guy who's gathering that data, tell him there's something wrong, and at the same time send a PDF explaining where the errors are occurring and why they're occurring. Okay, and this comes into our reporting portal. So again, it could be as simple as a trend graph that gets immediately sent back to the guy to say, hey, these features on your Lego man have got, in this case, we've got low CP, low CPK, the repeatability isn't good enough. Please examine. Okay. At the same time, we're maintaining and on boards and things like that. So actually merging this data really helps, because the trend graphs you see there of the CM of the Lego man are combining the attribute data, the measurements from the CMM, the measurements from the laser scan, and the data the guy has input manually. Okay, shall we?
Yes, perfect. Thank you, Ed.
Move on then, Marco. Yeah.
Yes, then we can move on to the really interesting part of this webinar, as far as I'm concerned, combining the quality data with the process data. So we've spoken about combining attribute and dimensional data. What we think is a real opportunity, a missed opportunity in most cases, is actually combining that data with process data and doing analysis and correlation on those two data types, the process and the quality data. So we've prepared or gathered some examples of those data. Here is just some example of the attribute data that can be shared with the system. We have some dimensional data and some process data. So here's the dimensional data example and the process data example. Maybe Ed, you want to add something else to this slide?
I would just say that the really important thing these days is to bring all of this data together. A lot of people are trying to do that in a lot of these BI tools. I've been using Power BI and Tableau a lot recently to do this. But what we found is those systems don't think in 3 dimensions. And actually the relationship between measured features, either between parts in an assembly or through an assembly structure, or their relationship to their process parameters, is actually very important. So looking at the patterns of holes, say, on things that fit together, or looking at the fit and finish of one part to another in 3-dimensional space using virtual fitting tools, is something that really enhances the quality data that you've got. You know, if you've measured the door from one factory of a car and the body from another factory in a car, and if you can fit all these things together in your software before the guy from the door factory starts shipping doors, you can save yourself a lot of money, because you'll know whether they fit or not. Okay, so it's very important to combine all this data, but at the same time be able to do all the 3-dimensional retransformations. And what we've got here is an example. I've we've got permission from the old guys at Saab to use this data because it's older data from the old Saab 9.3. In this case, we asked the system to look for strong correlations between different features, in this case just on the hood of the Saab 9.3. And I think you can see on the left hand side there's I think there's 20,000 possible combinations of all the features across this hood. And as you can see on the picture of the hood, some of those are actually relationships between features that were measured, so distances across, center points, patterns of holes. Okay, and the example I've got in the top right there is that actually between the midpoint on the center where there's a locator hole for the soundproofing and the far edge, we've actually found a very, very strong correlation. So what we know is that if we see on the hood stamping that this point on the far left is somewhat out, we know that the positioning of the soundproofing in the hood is going to be off center. Okay, now that's a fairly trivial example in one sense, but if you look in the bottom right there, what the system does is it learns about these relationships, all of these relationships that are strong on the hood assembly to the hood assembly, or on the hood assembly to the fender, or on the hood assembly to one of the stamping parts that make up that assembly. All these strong correlations can be exported and then registered in the database or in a database. Okay, so I move on there, Marco. And I think I've got another, yeah, this is another example of using that sort of correlation study. In this case, I got a load of measurement data from some Lego men, and we were able to extract from the injection molding machine a load of parameters. Okay, I've just, you can see a few of the parameters there, and then we ran a correlation study. And what we're seeing is strong correlations, in this case, between the media temperature and the left arm. And again, all of those things will get exported, and we'll use these correlations to teach our quality management system about the strong correlations we know about, and over time it will learn, and then we can do what we can see on the next slide, which Marco, I think, yep. So I'd say learning about relationships here, what we've been working on over the last couple of years is what are the sources of influence that we can find in your quality data that can impact your quality. How can we register all those so that database or the system learns, and then how do we actually push that out in a easy to understand manner? Okay, now at the moment we're using these 6 different sources of influence. Okay, the simple one is XYZ position. You know, if we have a hood assembly and we measure in the top left corner, we'll probably have measured the same position or very close to that position on the stampings and on the sub-assemblies. So having a system that automatically registered all those close positions anywhere in the product assembly is a good start. They're almost certainly going to be a relationship, and we can show clearly as you go up the assembly structure where a problem is starting to occur. You know, you could see no problems on the stamping, no problems on the sub assembly. You come to the major assembly, oh yes, that's where my quality problems are starting to occur. Okay, We've linked up with tolerance stack analysis suppliers, such as I've mentioned Siemens with their VSA tolerance stack studies. RD&T is another tolerance stack company. And again, these are predictive tools that are used in the design process that predict that locator hole A will influence the position of the gap on the final assembly of your Lego man. So we can pull all of that in. We can run the correlation studies we've seen before. We can script those so that at one particular company, we do have a regular scripting that goes through and looks at over 5,000 different parts, looking for correlations across those parts. I think in total, there's something like 20,000 features, all of which get correlated to each other, looking for strong relationships. Okay. And then we're using more complex and modern pattern analysis. We're working with a company called Rulex to develop the sorts of pattern analysis and linking tools that can be used to register what links to what. A lot of this is based around neural net stuff. A lot of it is based around some advanced correlation tools. And some of the things we're also looking at are applying Fourier transforms to the quality data to look for cycles in the quality data. You know, we can push the quality through a Fourier transform and say, oh yes, we have a repeating pattern at 100 feet or every 100, or we have a repeating pattern every Friday. Okay. And at the same time, we can take the exports from things like IBM Watson and register those as influence. Okay. So one of the things we're doing a lot at the moment is looking at vibration analysis from, say, condition-based maintenance. This would traditionally be fed into your maintenance planning tools, but we can register that as an influencer on the quality. And this allows us to work both ways. We can use the quality measures to message the maintenance management system, or we can use condition-based maintenance parameters as they come in to say, hey, look, expect to see poor quality in the near future. So the whole idea of this is that we can register sources of influence, and then we have easy tools to allow you to visualize what's going to happen now that we've registered those influences, which is on the next slide. Okay, here's a few examples. This is real data, but I had to replace all the CAD and change all the field names and everything so that we can show it to you. Okay, the example here is we have a gap and flush condition on the hood fitting of a car. The system has registered that on the final assembly, we have 4 possible sources of influence for that gap. And as it turns out, the VSA study, well, it was RD&T in this case, the RD&T study shows us that the front pin for the mounting point on the hood actually influences the gap in the corner. So we can put all this, we can also pull in all the data for the body in white. And it goes on. If you look in the top right there, we know that the flush influences that have been predicted just by being close in XYZ position are on the final assembly, the hood outer, the fender outer, the body in white, and there would probably be some others because this system grows over time. As it finds more correlations, as it finds more features being measured, that are close in XYZ position, they get added to the reports. Okay, and I think the next example is a really good one from the Lego guys, and is my final example actually. So in this case, we've asked the system to look ahead and predict if current trends continue, when will features fail? And in this case, we've said, look 100 units ahead. If anything on this Lego man is going to fail in 100 units, put it on one page. Okay, so there are actually several hundred things measured on this Lego guy. It's found 5 where we're predicting failure in 100 units. It's also found a declining slope on the feed pressure. So all of that just gets pushed onto one report. Okay. Now, traditionally in quality management, 1, it wouldn't predict ahead. 2, you'd get a 200 or 300 page report with all of the features for the Lego man, and somebody has to go through and analyze that. And what we're trying to get away from here is doing that manually. We want to predict ahead and move the analysis into the software. Okay, if we move on here, each of those concern items, we're going to email somebody. We'll register who is responsible for that process in the database, and we'll send them a full statistical analysis of that particular feature as a page. And of course, the user will decide what they want to see on that page in terms of statistics. But at the same time, we're going to reach into our relationships part of the database, and we're going to automatically create a graph showing any features anywhere on the structure of this Lego guy that are related to this body feature, and at the same time, any process parameters that have been shown as related to this particular feature. Okay, so we end up with a single page report that very clearly starts to show where the problems are, because we've related all of our parameters and features together. And in this case, it's very obvious that the drop in process pressure seems to be the cause of a number of quality issues in this Lego man assembly. Okay. And as more and more data is collected, and as the correlation and the automated systems look for more relationships, the system becomes incrementally better at finding the root causes of your problems. And as we saw in our first example, those root causes and concern items are pushed into the attribute system. That generates a defect log, and as the defects are cleared and the problems are solved, we record how they solve the problem, and that becomes our knowledge base for the future. Okay, so as your record of fixes starts to grow, instead of just showing, oh, here's a possible link, it's here's a possible link, and the last time this happened, we did this. I think that was really all I had to say on this one. Do you want to move on there, Marco, and take over here?
Yes, perfect. Thank you, Ed. So just a short conclusion, just a couple of highlights. So by combining the available data, the quality and the process data, we see a possibility to reduce the cost of quality and improve the quality and the actual output. Like Ed explained, by applying modern analysis techniques, you can reduce reports to only show the items of concern, as shown on the previous slide. By applying machine learning and linking to AI systems like IBM Watson, it's possible to predict failure and rapidly get to the root cause of failure and issues. And future work will enable the system to suggest actions to prevent failure, where future work is a relative term. It's already possible, but it can be enhanced quite a bit, of course. So that concludes our presentation part of the webinar. Are there any questions, Olga?
Yeah. No, I don't see any questions. So I think we can close the session, or at the same time invite people to another webinar, which will be on the 29th of April. It's about a no-code approach to manufacturing data integration. So I would like to thank you for joining us today and for staying with us till the end. I hope you have a nice rest of the day, and do not hesitate to reach out to us, either to Marco Naninga or Edward Morris or Mark Bolton, who is the director of the ATS in the UK. Oh yeah, thanks. Here we have the email addresses. Right. Okay.
That's great.
So
Okay.
thanks again, and goodbye for now.
Yes. Thanks everyone for listening. Bye.
Thanks all. Have a good day.